Good morning, everyone. I'm Terje, and today I want to give you an introduction to nonlinear material behavior. And I will use the solver SOL601, which is basically the Ardena implicit solver in NX. And I will use a model from the NAFEM's book, Introduction to Nonlinear Finite Element Analysis. And this model is 3 bars with 3 different yield strengths. And these 3 bars are loaded with a load, and gradually they start to yield. And then we will see what happened with the tangential stiffness. We often use the term tangential stiffness when we talk about nonlinear analysis. And this is part 1 of my introduction to nonlinear finite element analysis, which is nonlinear material. The next video I will release is focusing on nonlinear contact behavior. And then the final one will focus on nonlinear geometry, including the effect from follower loads. Follower loads also cause follower stiffness, as you will see. This is the model, and as you see, at the lower end we have a rigid bar, which is connected to rigid ground through 3 different beams. And these 3 beams have the same cross-section and length and E modulus. The only difference is that beam number 1 has a lower yield stress than beam number 2, which again has a lower yield stress than beam number 3. And the yield stress for these beams are 200, 300 and 400 megapascal. And the stiffness in each beam is EA divided by L, obviously, and they will then have a total stiffness of 3 times EA over L. And that's before any yielding start. But as I said, first beam number 1 will start to yield, then number 2, and then number 3. And then we will see how the tangential stiffness will change. The NAFEM book proposed that we use beam elements, but I've chosen to use solid meshes or 3 beams meshed with solid elements. And the length of the beams are 50 millimeters. The cross section is 10 by 10 millimeter. And I meshed them with 5 millimeters hex 20 elements. Then I created one material model for each of the beams. They are identical except that beam number 1 has a yield strength of 200 megapascal, the next one 300 megapascal, and the last one 400 megapascal. And I used a bilinear elastic perfectly plastic material model with no hardening. Then I created a rigid element connecting one end of these beams. That means I can apply a prescribed displacement in the master node of this beam, and they all will then deflect just as much. And as you see here, I've applied a prescribed displacement in this master node starting from 0, and then after 10 seconds it increases to 5 millimeter. If you apply a deformation of 5 millimeter, you will see that necking will start to occur. In this example, you can apply 0.12 millimeters. That's enough to start yielding in all 3 beams. So I propose that you start with that deformation. However, if you make 3 beams with different dimensions or different yield stress, then you probably have to adjust this number. And also you might have to adjust the number of time steps that you use in order to apply the load. I want to run a static analysis, so I applied the prescribed displacements during 10 seconds, and I applied them in 100 steps. That means the time increment, that means pseudo time, because this is not really a dynamic simulation, is 0.1 second. So that means I will have 100 time samples when I display my results. And those time steps or time intervals are given here in the solution setup case control. Then I applied fixed constraints on the other end of these 3 beams, fixed to rigid ground. So that's basically my model in NX. And this is my material model. This is for beam number 1, which has a yield stress of 200 megapascal, E modulus of 200 gigapascal, and a Poisson ratio of 0.3. And I wanted to have no hardening. That means a bilinear, elastic, perfectly plastic material you have the elastic part and the perfectly plastic part here. The first thing I'll do is to select engineering stress and strain, because I don't have necking here, so that's convenient. And then I use a stress strain curve. I add a stress strain curve as a table field. And here you see how I do it. I start with the first point, which is 0 and 0. 0 strain gives 0 stress. And then the next point is my yield point. And here you see I've used a yield stress of 200 megapascal. And then I used the E modulus. I simply divided by the E modulus to get the strain where yield starts. And that will be 0.001. That is right here. And then I can give an arbitrary point for a higher strain ratio, like 1, and the same stress level, 200 megapascal, or yield stress. So that means this is perfectly flat. There is no hardening at all or softening. And I applied the material for beam number 2 and 3 the same way, but I used sigma 2 300 and sigma 3 400 megapascal. I will soon show you how to set up and run this simulation in NX, but first let's have a look at the results. I applied a total deformation of 0.12 millimeters in 100 increments. And when I animated the results, I noticed that after 42 increments, which represents a deformation of 0.05 millimeter, I reached a stress level of 200 megapascal in all 3 beams. They reached the same stress level simultaneously because the E modulus and the physical dimensions are the same. Then what happens is that beam number 1 will lose its stiffness, and that means that the total tangential stiffness for these 3 beams drops from 3 to 2 EA over L. So now it's only these 2 beams that can carry more load. And then what happens next is that with a further increase in deformation, that after 63 increments, or a total deformation of 0.756 millimeters, I've reached a stress level of 300 megapascal in these 2 beams. And you can notice that beam number 1 has still the stress level of 200 megapascal, which is the yield stress of this beam. Then this beam number 2 will lose its tangential stiffness, or stiffness. And that means the total tangential stiffness of this system drops from 2 EA over L to EA over L, because from now on it's only beam number 3 that can carry more load. And this is what finally happens. After 84 increments, or an applied deformation of 0.1 millimeter, I reached a stress level of 400 megapascal for beam number 3. While the 2 other, they will still have the stress level representing their yield stress. And then you see this one has a stress of 400 megapascal, and then it's also start to yield. And that means that the total tangential stiffness has become 0, and this system is not able to carry more load. The effect of a nonlinear material behavior can also be visualized in a graph in NX. And here you see I plotted the applied displacement versus the reaction force in the RB2 master node. And here you see what happens. Until this displacement, that means roughly 0.05 millimeter, I have no yielding. The stress levels are below 200 megapascal in all beams. And then my tangential stiffness is 3 EA over L. Then when beam number 1 starts to yield, it loses its structural stiffness, and the total tangential stiffness drops to 2 EA over L. And then the next thing is that beam number 2 starts to yield, and then it loses its stiffness, and the total tangential stiffness has a further drop to EA over L. And then after 0.1 millimeter applied deformation, also beam number 3 starts to yield. And you see here that the load level capacity has reached its maximum, so a further increase in displacement will not increase the load carrying capacity. And then you can say that we have reached a limit point. And that's also the reason why we applied deformations here incrementally instead of incrementally apply a load. Because if you apply an incrementally deformation, you see that you will get results for each step. However, if you use the force incrementation instead, it will run quite well until you reach this limit point. But after this load level, there is no capacity in the bars anymore, and then you will end up with a singular solution because you have no stiffness. So you have to take care of that when you run a nonlinear analysis with material plasticity like this. It's almost of the times more reliable to apply deformations incrementally than forces. Here is my CAD model, and it's very simple. I just made a sketch 10 times 10 millimeter, and I used 50 millimeter extrude, and I patterned the geometry. So let's have a look at, we go to pre and post, and we open the FEM model. And here you can notice that I turned the models around so that set direction, positive set direction, is pointing downwards. And here you see that I meshed the models with solid hex elements, and I have 3 different collectors. I put first all metal elements for beam number 1 under solid yield 1, and it has the property of 200 megapascal in yield, as you see here. This is the E modulus, the Poisson ratio, and here I used engineering stress and strain, and we can have a look at the tabulated data: 0.0, 001, 200, and 1, 200. That's the properties for beam number 1, and that's why I put them under collector yield 1 here. And then for beam number 2, I used yield number 2 properties, and we can have a look at them as well. That's the 300 megapascal yield stress. It's the same E modulus, the same Poisson ratio. I use engineering stress strain, and I can have a look at the properties. It's 0.0, and the yield point is 300 megapascal, and if I divide it by the E modulus, which is the same for all beams, I get this strain, 0.0015. Then I added another strain point with the same stress level because it's perfectly plastic. And I pretty much did the same for the last beam, which has the property of 400 megapascal in strain or plastic stress. So these are my 3 collectors for these 3 beams and the corresponding material properties. Then I have an RB2 element in the lower end, and I applied the prescribed displacement in the master node of this RB2. So then let's have a look at the simulation file. First, I added the constraints, fixed constraint in this end, and then in the other end, I applied the enforced displacement like this. I applied 0, 0 in the X and Y direction and also in the rotational directions. And then I applied a prescribed displacement in the Z direction. And I did it like this. I applied it as a function of time and length to be the prescribed quantity. And at time 0, I applied 0 length, and at 10 seconds, I applied 0.12 millimeter. And this is how you have to do it in order to run a nonlinear analysis and apply an incrementally load. If you applied a constant value here, it would be put on the first increment. It will not be gradually applied like I want to. So those are my loads and boundary conditions. And then I applied or selected as SOL 601 solution. And here you can see the properties. There is nothing special here except case control. Here I applied an output request, applied enabling force requests, and I don't think I asked for more than that. No, it's pretty much the standard output. But here is the important thing, the time step intervals. I applied a time step interval. We can have a look at it. I want to apply the load in 100 increments, and sometimes you have to change this number. You can probably use fewer steps here than I did, but I thought 100 was an okay number, and it did run well. And then I applied a time increment of 0.1, and that means my total simulation time will be 100 times 0.1. That means 10 seconds. And if you remember, I applied the enforced displacement during 10 seconds. So then I will, during that period, apply all the formations I want to apply. So then, after creating this time step, I have to apply them by pushing the add button here. So it has to be down here. And if you do that, you will see that a number 1 here will pop up. And that means I applied my time sequence or time incrementation. When my applied displacement is small, that means 0.12 millimeters, like I do in this case, I don't want to initiate or apply large strains and displacements in the simulation. And that's partly because in the NAFEM's book, they assumed a linear relationship between strains and stresses, or displacements and strains. And also I used engineering stresses and strains in my inputs. So I keep them like this, not activated. And then we are ready to run. It takes a few minutes on my computer, and then we can open the results. And let's first have a look on the stress level. We will have a plastic nonlinear stress, elemental nodal, and let's have a look at the von Mises stress. Now we can run an animation. We can also create curves, but let's just step through the increments. And here we know that after 42 increments, we should have reached a stress level of 200 megapascal. Let's see here. Now we have step number 40, 41, 42. There we are. Now we see that the stress level has stopped here on a level of 200 megapascal on the first beam. And then we can step further. Now beam number 1 has no more structural stiffness, and let's increment this until we reach a stress level of 300, like we did here. Now we see that the stress in beam number 2 has reached the yield stress of 300 megapascal. So now it's only beam number 3 that still has its structural stiffness. Then we can increase when we increment up to 84 increments. The stress level should have reached roughly 400 megapascal, like there. Now we have. Now we see that the stress is 200 megapascal for this beam, 300 for beam number 2, and 400 for beam number 3. And now they all are in the plastic region, and they have all lost their structural stiffness. And they have gone through a change in tangential stiffness from 3EA over L to 2EA over L. And then finally, when also beam 3 has gone into plasticity, it has no more structural stiffness. And you can't increase, it doesn't increase its load capacity. So that pretty much wraps up my intention with this simulation, how to show how material plasticity will influence the tangential stiffness of a system. And this is, of course, a very simple example, but it shows the basic principles of material plasticity, and I hope you liked it.